choices. So before starting the lecture, we want to have a short recap of the quest algorithm, because during the weekend, as I said, we got a few questions regarding the method. So as I told you, the demonstration is not really fundamental during the exam. So I don't want to know all different passages to go from the maximization of the cost function GA to the formulation of the eigenvalue problem. So what we would like to know when you are at the exam, that you know exactly why we are doing an eigenvalue problem, what does it mean, and for example, you should know what are what is the dependency of this function of this matrix K with the attitude profile matrix B and the versors V and W, so the unit vectors that express the measurement in the sensor reference frame and in the inertial reference frame. One of these slides that probably was a little bit misleading is this one, because as I told you, I only gave you this formulation saying that S and X are function of these parameters S, zeta, and sigma that we have defined here, but I didn't give you an explicit form of this representation. The reason why we didn't give you this explicit form is because this quaternion corresponds to the solution when lambda is exactly equal to 1. So when you know that lambda is exactly equal to 1, you can substitute 1 here, and you can determine indeed that the quaternion has a form similar to this one, and you can derive by yourself the function of these parameters to S, zeta, and sigma. The reason why it is not really necessary, but if you want to do, it is a very interesting exercise, is because when you have to deal with a problem, a realistic problem of attitude determination, you have to be careful that lambda will not be equal to 1, because you know that there are different error sources in the measurement, so in your unit vector W, but also in the vector V, as we're going to see for the star triggers, because the knowledge of the inertial of the celestial body in the inertial reference frame is also affected by error. So hopefully these explain and what I meant here. So this slide is not really important when you want to do a method that basically enables the determination of the quaternion. So what you're going to do when you will have the exercise on the quest algorithm, you have to solve for the eigenvalue problem, find the value of lambda that is very close to 1. And with that value, you have to find the quaternion, because that quaternion is the quaternion that you are looking for, and is the quaternion that is going to maximize the function GA. Okay, so those were just...
I have a question about that representation of the final quaternion. Could you go back to that slide? Thanks. Isn't that a normalized quaternion, right?
Yes.
Okay. Then why S is not squared in the root?
Yeah, but as I told you, I mean, this formulation is not even probably correct. This is a normal vector, but S is a scalar. S is a scalar. So I think that X, so the vector X is basically, this is the scalar part. So S is the scalar part of the quaternion, and the X is the vector part. So basically, this square root is the sum of the scalar part plus the norm of the vector part of this quaternion here. So basically, you divide by the norm of the quaternion in order to have that the quaternion is indeed equal to 1. So yes, it seems that this squared is outside the square root, but basically this is the norm of the vector of the quaternion, and this is the scalar part of the quaternion. Okay? That was your question, correct?
Yes, I was just asking myself why S is not squared in order to be a norm. I imagine for a fourth dimension vector.
Okay. No, but because basically, so this probably is misleading because this is the norm of the vector. So I don't, probably is not even this one, it is a square. So that's the reason why I didn't check this expression. The only reason why we, so that slide was originally in that, in the original version of this part of the course is only to show you that if you choose a lambda equal to 1, you're able to express the quaternion with this simpler form. So basically here you have that this S, so the scalar part is only summed to the norm of the vector. Okay. So okay, so you're doing a scalar plus the norm of the vector. So probably this squared is not even correct indeed. But I'm not able to to change the slide because I have a version that basically is not able to change the format. So I can correct that. But as I told you, it's not really the main part here. The main part is that in principle, you're able to determine Q if you know that lambda is equal to 1. But it's not really what you need. What you need is to find the quaternion iteratively you have to find lambda iteratively in order to know which is the lambda you need. When you know that, you find the Q. So in that case, the Q will have a different expression. So every time we will have a different expression because lambda will be always different. So you don't need to know an analytical form of Q. It's not really the main point of the quest algorithm. The quest algorithm is that once you know lambda, you are able to determine Q. Okay, so let's go back to the star triggers because as we have seen, so far we have introduced determination attitude determination algorithm that give you the possibility to have a single frame determination. So means that you have measurement at a certain time that give you the attitude of the spacecraft at the time of your observation. So it means that if you have, for example, star trackers, you're going to use star trackers in order to determine the position of, so the orientation of the spacecraft at the instant at which you are collecting the measurement from the star tracker. Quest algorithm is probably the best approach because, as I told you, if you have multiple observations, you are able to weigh those observations. But today, since we are going to conclude the star sensor part, we are going to introduce the gyroscope. You're going to see that between a measurement of the attitude of the spacecraft from star trackers, you need to know you can indeed use the gyroscopes to determine the evolution of the attitude of the spacecraft between two observations. In general, gyroscopes are not really useful when the star trackers are already in operating. So as we have seen, the star tracker was able already to identify and acquire the stars. And so it is in the star tracking mode. So when the star trackers are already tracking a star, in that case, the gyroscopes are not fundamental. So one of the questions that I got early this morning was indeed why we need to know the attitude from the gyroscopes in order to, for example, initialize the star sensors. So the main, so the four steps of operation of the star sensor attitude termination for software are reported here. As I said, you have a star catalog upload, star identification and acquisition, star tracking, attitude processing and refinement. So when you have to start the operation of a star tracker, so you have to collect your first measurement. Since you are not able to load all the sky maps in your software, you need to load in your software the portion of the sky that you are going to look at. So you need a preliminary knowledge, as I started to write here, a preliminary knowledge. You need a preliminary knowledge of the attitude, okay? So you need to know the preliminary knowledge of the attitude from another sensors that is, of course, the gyroscopes. The reason I'm saying that is, of course, the gyroscopes, because as we're going to see today, the gyroscopes give you information regarding the spin of a spacecraft. So the angular rotation of the spacecraft. And you can use this information. You can use this information in the attitude equations here. So if you know the omega, so how the angular velocity of the spacecraft is evolving during time, you are able to integrate this equation, and you are able to know how the attitude of the spacecraft is evolving. So the Quaternion, so the gyroscope give you an important information where you don't have any information regarding the, for example, stars or the Earth and Sun, because gyroscopes are always able to give you a measurement of omega. The problem is that why we're not always able to use gyroscopes, for example. Well, as we're going to see, gyroscopes are really affected by many error sources. And the two main parameters that models the errors of the gyroscopes are bias and drift, as we're going to see later, maybe tomorrow. So going back to the so the preliminary knowledge of the spacecraft, since we know from the gyroscope, for example, which is the initial orientation of the spacecraft, we can indeed load the portion of the sky that is the one that we're going to look at. So what happens here is that the gyroscopes give you a preliminary knowledge of the attitude. So we are able to determine which is the portion of the sky we're going to look at. And as we have seen on Thursday last week, we are able to identify and acquire the first measurement of of the stars. The problem is that when you have to upload the map and you have to identify and acquire the stars, this operation takes about from a few seconds. So from 3 to 5, also to 10 seconds. So for the operation of a gyroscope, you're not able to do these 2 stages every time that you need an observation from the star tracker, because this operation indeed is really time consuming. So that's the reason why, as we have seen on Thursday, you need to do that at the beginning of operation of a star tracker. So you determine you identify the stars by using, for example, the angular separation match, or even better, the polygon match of a star constellation, in order to determine that you are exactly looking at the stars that you have on the map that you have loaded before. This first operation is important because once you know that those stars are in your field of view, you can use these stars to track those celestial bodies during the evolution of the spacecraft altitude. That's the reason why afterwards, after the star identification and acquisition, we have the star tracking. Star tracking means, let's do that here, that once we know that in our field of view, so let's redo the, let's assume that now S1, S2, and S3 has been identified. So we use, for example, the polygonal match in order to determine that those stars are indeed in our field of view. So basically, let's assume that we've done this polygonal match, and we know exactly that those stars are the one that we are looking at. As we have said last week, the properties of the stars that we have to take into account are the magnitude of a star, apparent magnitude of a star, and the other is indeed the spectral type. So assuming that your polygonal match indeed checked that those stars are the one that we need to control, what happened now is that the star tracking is definitely easier than that one, because what we are going to do here, let's say that we take the stars at a different time, T1. So in our field of view, now the 2 stars, so the 3 stars, have moved from this point to this one, to this point to this one, to this point to this one. So we are able to only determine which is the delta, so the variation of the position of the star in our field of view, in our CCD. This is, of course, this update is definitely faster. So that's the reason why when you were able to determine indeed the position of a star in your field of view, you are able to track that over time. For example, with a larger sampling rate, let's say 10 Hertz. So what that means that 10 times per second, you are able to determine which is the movement of the stars in your CCD. So you're able to get every 1/10 of a second a measurement of the star. Another reason why you need more stars in your field of view than 2 or just 1 is that when you are in the star tracker mode, what can happen indeed is that, let's say that you have after, okay, in this case it doesn't occur. But let's say that, let's say that you are over here, so it's a little bit shift. What can happen is that at a certain time, one of the three stars can be outside your field of view. That, of course, can be a problem. So another important thing that the star tracker has to do during the during the star tracking mode is that when one star is exiting the field of view, has to check in your CCD that another star is indeed within your field of view. So you can substitute your stars S2, for example, with an S4. In that case, you are able to still keep the polygon match of the star. And so you're able to be sure that you are looking exactly at that object. And so that is an important property, that if you have, for example, two stars only, and you have that at a certain time one of the two stars is exiting from the field of view, you can have a possible ambiguity because you have only a single star in your field of view, and so that could indeed induce significant errors in your measurements. So this is the third step. That is, of course, joint is done jointly to the attitude processing and refinement. So once you're able to track the star position in your CCD, you are able to process and refine your attitude every single time. For example, using the Quest algorithm. At a certain time, delta t, so after delta t, you have t1, you recheck the position of the stars, you have an updated version of the vector S, and you reprocess the measurements in the Quest algorithm.
May I ask a question?
Yes.
Would the star trackers be in star tracking mode throughout the entire mission, or is it intermittent?
So in principle, you should have start rigging for very long time. But of course, there are many problems. For example, star triggers also are power demanding. So you need to be sure that you're always able to provide power to the instrument. So let's say that you have an orbiter around the planet in the solar system. There are possible periods in which you are not able to use all the star triggers. And so in that case, you have to, when you lose the star tracking mode, you have to reinitialize the instrument. So redo the star catalog, star identification. So you have to respend, let's say, a few seconds, let's say 10 seconds. And after that, you restart the star tracking. So hopefully you are able to do that continuously over time. But in practice, of course, you have a lot of possible interruption of the star sensor operation, but that will not be a problem. The main thing is that you need to keep the star tracking mode. For example, during if you have specific duties for operations or let's say you have a communication satellite, that during communication the star triggers is working. When you don't have, for example, important operation, you can indeed rely on a lower attitude accuracy. And so probably in that case, one of the two star triggers, one of the three star triggers is not operating. And so when you are going to reuse that star trigger, you have to reinitialize the instrument, so reload the star catalog and the device. So in principle, you should always work with the star tracking mode. but there are different situations during a mission that is not really possible. So and the other thing is that one could be wondering if you are why you don't need to reload the map every time, why you need to do this start tracking, because of course, as I said, the main problem is related to the time that you need to reload and re-identify the stars. But also it is a problem, a computational problem. So every time that you have to reload a map, that means that you have to do much more powered, basically computational demanding processes on your onboard software. So with the start tracking mode, as we have seen here, you need also only to take into account a specific portion of the sky. And so computationally is definitely less demanding. So in these software scheme of the star sensors also give you information regarding the gyroscopes. Because as I said, gyroscopes are important when you don't have accurate measurement of the attitude and you have to initialize your star sensor. But star trackers are also very important when are in the star tracking mode for gyroscope itself. Because as I said, gyroscopes are not accurate sensor on a long time span, because they are significantly affected by important errors in the temporal variation of the signal of the gyroscope. So for example, we're going to see that you have electronic errors or other source of errors that give you biases or drift that are modeled as a random walk. And in order to recalibrate this instrument, you can use your measurement of the star trackers, so the measurements from the star trackers, in order to recalibrate the gyroscope itself. So you can, with the extended Kalman filter, include other parameters in your solutions. That's what we're going to see on Thursday. When we introduce the Quest algorithm and the Triad algorithm, we have introduced those algorithms as a single frame determination software. That means that you are able to solve for the frame at that specific epoch, but also means that you are only able to solve for the parameters of the attitude, for example, the quaternions of the spacecraft. So you're not able to estimate additional parameters. If you use the extended Kalman filter and you combine measurements from the gyroscopes and measurements from the star trackers, as we're going to see, we're able to have a combined estimation of the attitude and also the parameters that model the errors of the gyroscope that we're going to introduce tomorrow. So this star tracking mode, it is important because provides the best knowledge of the spacecraft attitude, but also calibration of the auxiliary sensors of the attitude, as for example, the gyroscope. To conclude this part on the star tracker, since in the next hour we're going to introduce indeed the gyroscope, so how those instruments works and the main limitation of the gyroscopes, we have to introduce the other problem of the star sensors. What we have introduced now is indeed how to generate, so how to determine the altitude using the star sensors. But the main problem of all instruments, of course, are the error sources. And as I said, error sources are not only coming from the sensor itself, but also from the knowledge of the celestial body orientation. Here you can find indeed an image of two different star trackers that have been used in space. And as we have said, you have a shield from other sources of light, as for example, the sunlight, the moonlight, and the albedo of the Earth. You have this specific field of view, and this box includes indeed the optics of the instrument and the electronics. So in there you have the optical lens that focus the image on a CCD, and you have also filters that enables to only look at stars with specific spectral type properties. This table is let me see. Okay, are not the same star trackers, but are other star trackers that with specific properties. So when you are looking at those instruments, what you have to take into account are the main properties of the instrumentation itself. So first property is indeed the field of view. So it is the portion of the sky that you are going to look at from your instrument. The field of view is directly related to the resolution that you're going to have, because the combination of the number of pixels on your CCD and the field of view gives you indeed the possible resolution of your the possible accuracy of the altitude. Last time we have done the we did the example of a 5 degrees by 5 degrees field of view and a 500 pixels CCD, and we have seen that you have at least almost 36 arcsecond resolution. Usually what you have here, you have a number of, so a certain field of view and a certain number of pixels in order to enable a specific resolution of the accuracy. So since here I gave you the field of view and here you have the accuracy of the instrument, you can directly, you can roughly estimate what is the number of pixels that you have in your instrument. That could be a good exercise to just check if you got a good understanding. Another important properties of the instrument is the sensitive range of the magnitude. Be careful that uppercase M is the absolute magnitude, so it is a little bit different with respect to the upright magnitude. Anyway, larger number means that you're able to see fainter object. So it means that you have this range of magnitude that you are able to see with those instruments. The other important parameter is the update rate in Hertz. And it is basically what I have said before when I was talking about the star tracking. So if you want to have a measurement during star tracking mode, for example, the first two instruments give you a sample rate of 10 Hertz. That means that you can have every second 10 measurement of your altitude by only looking at the tracking mode of the stars. For these sensor, you can have, for example, a double mode or 10 Hertz or 5 Hertz. The other important parameter is indeed the acquisition time. The acquisition time is related to the time that you need to identify and acquire the stars. As I said, those are around a few seconds. For example, these two instruments have an acquisition time of 6 and 5 seconds. The other important parameter that you have to take into account is the maximum number of stars. Larger is the number of stars, larger is the computational operation that you have to do on your software. So you have to have softwares that are able to process those number of stars. But if you have a larger number of stars, as you can see, you can also have a better accuracy, because this accuracy is not only related to the number of pixels, but is also related to the sources, error sources that you have in your in your sensor. So when the exercise that I proposed before give you the minimum number of pixels that you have to satisfy those accuracies. But in general, these accuracies are also related to the error sources that you have in your instrument. So, for example, this one gives you a better resolution of the attitude because it is able to track a larger number of stars. The other important parameters that you have when you design an instrument is indeed the maximum power and mass. You can see that the number of these numbers are indeed very different, especially this one that has without the shade, so without the protection for other light sources, 8.2 kilograms. And this one with the shade is about 3.6. So when you have to choose a sensor, you have to take into account all these properties. So for example, what is the accuracy that I need? I don't need an accuracy that is better than 10 arc seconds. Okay, so this instrument is really better because I have less mass. Yes, the maximum power could be also a very important problem. So we have also to take into account if the power that these instruments require is in line with my spacecraft. But you have to be careful that all these parameters satisfy your need. So I would stop here for a break because basically the last two slides before the gyroscopes are only related to the errors. So when you want to characterize, for example, the accuracy of the instrument, you need to take into account the errors on W and the errors on V. The errors on W are related, for example, to the different magnitudes and different spectral type of the stars. The errors on V, so on the knowledge of the celestial body orientation in the natural reference frame, are related to the catalog. So let's have a break here. So if you have any questions, we can discuss that during the break. We will start with that part later, and we will also introduce the gyroscopes.
Professore, scusi.
Sì.
Ma se io sono in tracking mode e devo cambiare la stella di riferimento, come diciamo quantifico l'errore nel mio modello?
Okay, so the question was regarding the tracking mode. So, so that's the reason why the question is if I have that one of the stars is going outside my field of view, how I am able to use another star, basically, right, in my model in order to not affect the solution of the autodetermination. So how I'm able to continue the tracking of the stars if one of my element is missing? Well, this is a fair question, of course. There is not a unique answer for that question because it depends on the instrument. And the dependency is indeed related to what we're going to discuss in this part of the lecture. So the main problem is that, of course, for example, in this case, you have that S2 is outside the field of view, and you have only S1 and S3. So you have to be, in this case, what happens is with a re-identification of one star, for example. So it is similar to what you had in the first two stages, that you need to load the catalog and the star identification. The main difference here is that the map that you have in your catalog now is more precise with respect to what you have when the instrument is initializing. Okay, so also the map that is uploaded from the instrument is uploading correctly. So what it means is that the software itself knows exactly what is the stars that are now visible in your field of view. So the accuracy, so regarding your question, what is the accuracy in the star tracking mode, depends on the accuracy of the star catalog and also on the filters that you have in your instrumentation, because if you have an error in the star catalog, that can affect that re-identification of a new star. But also, if you have possible errors in the magnitude and the star type identification of the star, that could also affect the re-identification of a new star in your field of view. So basically, that depends on the properties of the instrument. And the properties of the instrument are expressed, for example, in this table here. So you don't need to know these numbers. The only thing that you need to know is that usually the star trackers have errors that are related to the magnitude of the stars that you are looking at. And this error can be defined as a static bias or a standing random noise. So this is a static bias on your measurement, and this is a random noise, for example, a Gaussian with a Gaussian representation that give you the possible errors that are given by a star with a magnitude between of 3.0 or 5.5 magnitude of the star. So you have to be careful that every single star with different magnitude can give you a certain source of error in your S. So you have to take into account that when you do the re-identification of the star, so in the re-identification of the star, you are affected, you can have an error that can affect your measurement by providing an error in the attitude reconstruction of, for example, in this case, 4.5 arc seconds or so on. Those are real numbers of a realistic instrument, but you can find that for other instruments, because basically when you do a final check on your instrumentation, you do laboratory test, and you are able to determine for each magnitude which is the amount of noise, the amount of error that you can expect. So what happens here is that you are able to determine, for example, for each magnitude of the star that you are looking at, what is indeed the error that you expect. So the differences between the two is that the first table is related to the star position accuracy. So is basically related to the catalog error. So for each star with a specific magnitude, there is an error in the position of the star that can give you these error sources here, this error sigma here. If you have an error in the magnitude of the star, you can have, for example, a mismatch. So basically, when you want to detect a certain star, you have to be careful that the magnitude of the star that you're looking at can be affected by an error of about 0.24 magnitude. What does it mean? That if you have stars with a magnitude that differs by 0.1 apparent magnitude, that those two stars can be indeed can provide ambiguity. That's the reason why when you want to identify and acquire stars, you need to use multiple stars, because even if one star can be basically confused with another one, if you have a configuration of multiple stars, this error can be definitely lower. The other error that is also related to the magnitude of the star is related to the star position. And the star position is given basically, so basically is your V in the VABA problem or the triad problem. The knowledge of the position, so the orientation of the star in the inertial reference frame, is given by the star catalog. One of the main star catalog used, for example, by ESA, is the eParco star catalog. What we're going to see on Thursday will be a realistic scenario of an orbiter, Baby Colombo, that will be in orbit around Mercury in 2025, and will use indeed a common active determination software that is based or in a quest to a quest algorithm or to extend a Kalman filter to determine the attitude. When you want to, what we are going to simulate in this exercise is that you have all the four processes that we have seen so far. So you have to upload the star catalog, that is your eParco star catalogs. You do the identification of the stars and the star tracking. The problem is that you have to be careful that your star catalog is accurate enough, because as we said, the sensors can give you errors given by, for example, the ambiguity of the stars if the magnitude is not measured correctly. But the position of the stars can be also wrong, for example, if you have sources of errors given by, for example, the parallax or the proper motion of the star, or as we are going to see, also the aberration. So when you have a star catalog, you have the catalog epoch at which those stars orientations are referred to. The reference system, that is the inertial celestial reference frame. This was published in 1997, but you have a much more recent eParco star catalog. And you have these important properties of the catalog. For the main properties is the median precision of parallaxes, so give you the precision of parallax errors that you have from the stars, that I'm going to explain in the next slide. The other important thing is the proper motion. The proper motion is also related to the fact that stars are, of course, celestial bodies at different regions of the universe. So you have to take into account that there are stars farthest than others. And so you have to be careful that one star can basically apparently move with respect to the background. This is indeed the precision of the proper motion. This is an important property because if you have an error that does not take into account the fact that one star is closer to us and so is apparently moving with respect to the background, when you are trying to determine the vector v, that would be affected by an error that in this case is related to these 0.88, 0.74 milliarc second per year. The parallax, let me show you this figure. So the proper motion, as I said, is indeed the apparent motion of a star with the background. So all the stars have space velocity, and if one star is closer to us with respect to the background, what you're going to see is that this star is going to move with respect, for example, to this quasar that is very far from us. And you have to take into account that, because if you don't take into account this proper motion when you are doing the measurement of, so the active termination, that could affect your measurement. The other property that is cited in the star catalog, it is the stellar parallax. For example, if you are in cruise, let's do the example of Baby Colombo again. You know that Baby Colombo is indeed orbiting, so is going to from the Earth, and as last week has done the flyby of the Earth. So basically is following a trajectory initially that is close to the trajectory of the Earth, with a mean distance from the Sun on 1 AU. During each period of the cruise, you can see that this near star not only has a proper motion because it's moving differently from the others, but also, since you are looking at that star at different point of your orbit, you're going to see an angle, a different angle with respect to distant stars. So if you're looking at the stars from this position, you're going to see that this star have a certain angle with this one. If you have if you're looking at the same star from here, you're going to project this star in a different position with respect to distant stars. So you have to take into account the stellar parallax, and the star catalog give you this information. So with respect to where you are in the solar system, you are able to determine indeed this position. The third one, source of error that is given by, for example, the knowledge of the orientation of the stars in the inertial reference frame, is the aberration. However, this one is not related to the star catalog, as you can see. The other errors are not really important for us. But the aberration is not related to the star catalog, but is related to the motion of the spacecraft. So since the spacecraft is moving with a significant velocity, we have to take into account that when it is looking at a star, it is going to see this star with an apparent position, because for him, for the spacecraft, for it, the star, it is in this apparent position. When you are, for example, moving in a planetary cruise, you have to be careful that these planetary spacecraft can indeed aberration errors of about 20 arc seconds. And when you are in the LEO orbit, this will be lower. So you have to take into account that when you are moving across the solar system, the velocity of the spacecraft can indeed provide this aberration effect. That has to be taken into account when you load your map of the catalog of the stars. So those are errors that you have to take into account in your measurement. These two, so proper motion and stellar, are given by the star catalog. The aberration is a different error, and it is given basically by the motion of the spacecraft. So this concludes the star tracker part, and so we were not able to quantify. So we quantified the errors, for example, given by the parallax or the proper motion of when you try to determine the inertial orientation of a space of a celestial body. You can compute, for example, the error of the aberration if you are in orbit around Mercury, Venus, or in cruise, or around the Earth. We already gave you these numbers, but you have to take into account that usually you know what is the velocity at which you are moving, and so you're able to account for aberration. So those error sources affect your V. When you do the matching of a star, so you're trying to determine the position of the star in your CCD, that all these error sources given, for example, by CCD accuracies, or for example, when you do the matching of different stars, that will give you an error in W. So what I mean here is that if you are misplacing, so the CCD is misplacing S1 by 1 or 2 pixels, this is a direct error in your S, and so in your W. Okay, so let's start the other important sensors that you have for inertial, so for a spacecraft that has to know the orientation with respect to the inertial reference frame, and those are the gyroscopes. Probably you are more familiar with mechanical gyroscopes that basically are based on the fact that you have a moving part, for example, a rotator with a high frequency rotation that give you a stability, so a large angular momentum. And so you know that when this angular momentum, so you will have the conservation of the angular momentum, and your axis of rotation represents indeed a reference of your inertial reference frame. However, in space, so you usually tend to avoid to have movable parts for many reasons. The main reason it could be indeed that those mechanical gyroscopes are affected by significant error sources that increase significantly over time, and that will be indeed and also are affected by vibrations and other problems that you want to avoid during the operation in space. So what we are going to see focus in this course will be 3 types of gyroscopes. So the first 2 types are called laser gyroscopes. The third one is a newer type of gyroscopes that is called resonant hemispheric gyroscope. And it is based on a different principle that we are going to see tomorrow. So today we're going to focus on the laser gyroscopes that indeed represents a concrete instrument that is important to determine the inertial reference frame of, so the orientation of a spacecraft with respect to inertial reference frame. The 2 types of gyroscopes that we are going to see today are the ring laser gyroscopes and the fiber optic gyroscopes. So the 2 are a little bit different, although they are both based on the Sagnac effect. This Sagnac effect I'm going to introduce a little bit later, but enables to use interferometry to determine the angular velocity of the spacecraft. So as it is highlighted in this slide, you know that you have to always take into account that the gyroscopes will be always used jointly to star trackers. As I said, gyroscope give you the attitude when you don't have the attitude termination from others more precise sensors. But also star trackers give you the possibility to calibrate the error sources of a gyroscope during star tracking mode. So we reported here, for example, a reference. So if you want to have additional explanation regarding laser gyroscopes, you can find these two references that give you much more details of what we are going to discuss during this course. So what are the main advantages of laser gyroscopes? Why we need to use a much more complicated technology compared to mechanical gyroscopes? Well, you have a lot of advantages. The main advantages, as I said, is that you don't have any moving part. Also, it is, although the technology from the electronic point of view is, of course, much more complicated, it is a simple design. So you have to determine a very compact instrument that, of course, has to, for example, the ring laser gyroscope depends on mirrors. So part of those that gyroscopes could be indeed a little bit. You have to be careful because basically can damage during a specific operation of the spacecraft. So the design is simple, but also you have to be careful that the misalignment of mirrors, as we're going to see, could create problems. So in order, also it's very rugged. You don't need any maintenance costs. And one of the main advantages is that it is able to have a wide dynamic range. Although wide dynamic range means that if you have a variation of the orientation of the spacecraft with high frequency, you have to be careful that this high frequency indeed can provide, so you are able to detect these high frequency variation of the angular rotation of the spacecraft with the laser gyroscopes. But the main weakness of the laser gyroscope is that if you have a slow rotation of the spacecraft, there is a problem that is called lock-in that we're going to see later. That is basically related to the how the gyroscope works. The other main advantage is that it is a digital output, and also that you have a very fast update rate. As we have seen for star trackers, if you have a very high frequency rate of the measurements, you are able to determine the attitude with very small time integration steps. It also has a low cost, and the main advantage is that it has long and reliable uptime. In space application, when you try to design all kinds of sensors, the fact that it's very long and reliable, that is a very crucial properties of the instrument. So here is briefly basically anticipated what we're going to see in detail for the modeling of laser gyroscopes. But so we have to take into account that there are different error sources in both ring laser and the fiber optic gyroscopes. The main problem, as I said, is the poor long-term stability. So although it has a long lifetime, because of the electronics and other error sources, the stability of the signal tends to be biased and drift over time. And so that's the reason why you need star tracker to recalibrate this instrumentation. and also the biases represents an important error sources. Okay, so let's start to describe how a laser gyroscope works. As I said, laser gyroscopes, there are ring or ring laser gyroscope or fiber optic gyroscopes, depends on the same principle, is the Sagnac effect. So historically, the Sagnac effect is known because basically Sagnac was trying to determine the existence of ether in order to demonstrate that the light has to travel in a medium. Of course, as you know, this was not the test that he did was not helpful for that goal. That, of course, was not correct. But the main result that that experiment did was demonstrating the Sagnac effect. What is the Sagnac effect? Is that if you have that two, so it's not related to what you had for mechanical gyroscopes, in which you are looking at the conservation of the angular momentum. Here, you're looking at the fact that the speed of light is moving with is the same in all inertial reference frame. So assume that you have this path here. If you have one light beam that is going from here in a clockwise direction and the other one in the anti-clockwise direction, so in this direction here, the two, and you have that these two, so this ring is rotating with a constant velocity. Both beams are moving in this inertial reference frame because it's moving with a constant angular velocity at the same constant, so at the same velocity c. So the main purpose of the laser gyroscope is to use the Sagnac effect in order to see the interference of two signals that are moving counterpart, so in the opposite directions, and will form fringes of interference because the path where those two light beams are moving is rotating. So let's start with a simple case. So as I said, you have this circular path here. So here you have a light source, let's say a laser pointer, a laser source that generates a signal that goes through this beam splitter that you have here. So this represents a beam splitter. How the beam splitter works. So you have a light that is generated by the light source. Let's say that part of the light is reflected by the mirror that is here. So goes in this path of this circular loop. So it is moving anti-clockwise. The other 50% of the light is passing through the mirror. It is reflected by this mirror on the wall here and goes to this other mirror here and is reflected in this other direction. So you have that part of the beam is going anti-clockwise and the other part is moving clockwise. If you have that everything is still, so that this mirror, this beam splitter is still, and we assume, for example, that the detector is here as well. So basically here, not only you have this beam splitter, but you have your light detector. It means that the beam that is moving anti-clockwise and the beam that is moving clockwise are going to do 2 pi r. So the entire length of the loop. and they are going to approach the detector and with exactly the same frequency, because they are moving at the same speed. They moved with, so they are approaching the detector that is still with exactly the same. So what you're going to see is a destructive interference. So you're going to see that the two signals are exactly the same. So basically, you're not going to see any significant measurement. Well, actually, it would be constructive in this case. I mean, it would be destructive if you have a phase shift between the two signals. So let's assume that you have, for example, a difference by pi by two signals. So you have a destructive. So if you, when you try to match the two signals, you have that because the detector is still, you have everything is zero. So by writing these in this formula, these dph minus and dph plus are the distance that is basically done by the photon. So you have the speed light times t minus and c times t plus. The beam splitter in our case is still, so you have that this detector here is indeed still. So you have that is equal to 0 and it is equal to 0 as well. So when you're trying to determine which is the phase, you're going to see that indeed these two beams are going to interfere here, providing any information because omega is equal to 0. Once the detector is rotating, and this is the case when you have, for example, a spacecraft. Let's assume that you have mounted this path on a spacecraft, and this is an axis orthogonal, so it's the axis with respect the spacecraft is rotating. So now the spacecraft is rotating with an angular velocity omega. What does it mean here? That now the detector, with respect to the beam, is moving also clockwise. So it's going basically towards the signal that is moving anti-clockwise, but is moving away from the signal that is going from clockwise. So what does it mean is that the signal that is going anti-clockwise is going to approach the detector earlier. The anti-clockwise, the clockwise signal, so this plus here, is going to approach, is going to intersect the detector with a time later, so with a t plus. That's the reason why this is called t plus. So let's do some computation of that. That is really straightforward, because what you the only thing that you know is that if you sum the path that is given by the anti-clockwise signal and the detector, has to be equal to 2 pi. So if you see, for example, the signal has moved this part of the path, the detector this remaining part. So dph minus plus dbs minus is equal to 2 pi r. Same story for the signal that is moving clockwise, because the signal is moving in this direction here, and the signal is also moving in this direction. So you have to take into account that we are looking everything in the reference frame that is moving with the photon. So what you have here is that both are equal indeed to 2 pi r. So both signals are going to approach the detector when these two quantities will be equal to, so the sum of these two quantities will be equal to 2 pi r. So if we substitute these terms that we have here in this expression here, you can find that for the photon that is moving anti-clockwise, it will be equal to C plus R omega big omega is equal to 2 pi r. And the one that is moving clockwise, it is C minus R omega C plus. The reason why you have a minus here is because, as I said, you have to take into account that for between the photon and the beam splitter, here they are moving in the basically opposite direction. So basically this detector is moving away from the photon. That's the reason why you have a minus here. So from this simple expression, you can find T minus and T plus. So why we are so interested to know which is the delta T between the two signals? Because the delta T is directly related to the delta phase of the signal. So what we are going to see briefly today, and we are going to expand that tomorrow, is that by using the Sagnac effect, we are able to determine delta phase of the signals that is directly related to omega. Omega, as I said, is the angular rotation of the spacecraft along this axis here. So if we have that omega is equal to 0 and you do T plus minus T minus, what you have equal to 0. So you don't have any important signal. So that's the reason why this is so important, because as I said, if the beam splitter is not moving because the spacecraft is still, you don't have any signal. So let's use these two expressions to determine delta T.
I have a question. I guess,
yes.
When would the spacecraft ever really be still? Because isn't it always in an like rotating in some sense?
No, yes, of course. This is only a simplified example to explain how the gyroscope works. Of course, having a spacecraft that is completely still is only able, I mean, you're only able to have that during cruise, but it's not really an interesting example. So what I'm trying to explain here is that the principle that let the gyroscope works. So what I mean is that if you don't have any rotation of the spacecraft, you are not able to see any signal. In principle, as you said, the spacecraft is always rotating. And so what you are going to measure is indeed a delta T between the signal that is moving clockwise and the signal that is moving anti-clockwise, because they are going to be measured at the detector that is here. So if detector is still, will be here, so you don't have any signal. Since it is moving because of omega of the spacecraft, you are able to see a delta T. So if you do the difference between the two, you can easily demonstrate that since C is definitely larger than R squared omega squared, because the rotation of the spacecraft cannot reach the speed of light of the spacecraft. You can the speed of light. You are able to converge these delta T to this expression here. You can see that. By doing a simple difference between the two. So that would be indeed C squared minus R squared omega squared that is neglected. you have in this expression pi r squared. So you have the area of the path that you are took into account. And this is the main important thing. And that will be the main important thing why we are going to introduce the fiber optic gyroscope. The ring laser gyroscope indeed have a fixed A. And so the signal, so the delta T that you need to measure will be directly proportional to the area of the ring laser gyroscope. If you want to determine the optical path of the signal that you are measuring as the interference of the clockwise and the anti-clockwise signal is delta L. So you have to basically divide delta T by, so you have to multiply delta T by C. If you do indeed delta L equal delta T times C, you will get the optical path. The optical path is important because that will give us information about the phase difference between the two signals. So tomorrow will be clear what this formulation means. But so what we want to determine is indeed the delta phase between the two signals. The first result that we have found out is that the optical path of the signal that is given by the rotation of the spacecraft omega is directly proportional to the area of the gyroscope. So we have to take into account that. And tomorrow we're going to see that indeed the size of the gyroscopes is crucial to determine the signal that we get from the two interference light beams. So I will stop here.